Greetings and welcome to Mr. Van Lowe's poorly monetized, low-budget science channel. Do not click like, do not subscribe. Today we're going to talk about thermodynamics. This is IB topic B.4. So, learning objectives. By the end of this lesson, you will be able to explain the first law of thermodynamics and perform calculations involving heat, internal energy work, and temperature. You'll be able to describe open and closed systems. You will define thermodynamic processes including isothermic, isobaric, isovolumetric, and adiabatic. Finally, you will be able to interpret pressure-volume diagrams and relate them to the appropriate processes. So let's get into it. First, we have the first law of thermodynamics, in which energy cannot be created or destroyed, only transferred or converted from one form to another, including mass. Second key point for the first law is that the total energy in an isolated system remains constant over time. We will define isolated system later. Heat transferred in or out of a system is equal to the change in internal energy of the system plus work done by the system. Hence, Q is equal to delta U plus W. And this equation is nonsense until we carefully define our variables. So delta U is a change in internal energy. Q is equal to heat transfer, and W is equal to work done. This next then brings us to the Clausius sign convention, where positive and negative signs determine whether energy is moving in or out of each of these various options. Okay, so positive Q means that heat energy is transferred from the surroundings to the system. Positive delta U means that the internal energy of the system increases. Positive W means that the system does work on the surroundings. Conversely, negative Q means that heat energy is transferred from the system to the surroundings. Negative delta U means that the internal energy of the system decreases, and negative W means that the surroundings do work on the system. When in doubt, when you're attempting to set up these problems, just recall that the sum of energy going into or out of a system must be equal to 0. And that means that if we add up all of our terms here, they should equal 0. And that means that one or more of these must be negative. Okay. So next, let's define a closed system. This is a system that exchanges energy but not matter with its surroundings. So energy transfer will occur in the form of either heat or work across system boundaries, but the total mass of the system is going to remain constant. So an example of this would be a sealed container of gas undergoing compression or expansion, much like the piston diagram we saw earlier. An open system, then, is when a system can exchange energy or matter with its surroundings. And in this case, energy transfer can occur through heat, work, and the flow of mass across system boundaries. And the total mass of the system can also change as substances either enter or exit. A pot of boiling water is a good example of this, in which both heat and steam, water vapor, can escape. The mass will be contained within the steam, and it will be leaving the system. So just quickly to summarize the differences, closed systems involve energy transfer, while open systems involve both energy and mass transfer. Closed systems are usually easier to handle. So for IB Physics, we will deal with those due to the conservation of mass. For open systems, we probably would require the use of calculus to analyze them, and that's not really a thing for IB Physics. The universe is an isolated system, but inside the universe, our systems can never be completely isolated. Energy transfer is going to occur wherever there's a temperature difference, and you can find those pretty much everywhere. So we're mostly going to deal with closed systems, but you do need to know these definitions. Speaking of definitions, an isothermal process is a process in which change occurs at a constant temperature. So here we see two pressure versus volume graphs. These are occurring at different temperatures. And you should recall your ideal gas law equation, PV equals nRT. So these will both be affected by temperature, and that's what we see here. The red line has a higher temperature than the blue line. And when in doubt, you can graph these in Desmos yourself, which is what I did to produce this nice graph. Okay. For ideal gases, the internal energy is not changing, so delta U is equal to 0, which means that we can rewrite the equation for the first law as Q is equal to W. So the heat energy in or out of the system will equal the work done in or out of the system. The curvature of the pressure volume graph shown here is y equals 1 divided by x, then multiplied by a constant. Pressure is inversely proportional to volume, which is what we see here. So it all makes sense. All right, next up, we have an isovolumetric process. This is a process in which change occurs at a constant volume, and we can see that the volume is constant by this vertical line here. So that volume is not increasing or decreasing, and only pressure is changing. Since our volume is not increasing or decreasing, work is equal to 0. We'll talk about this a little bit more later, but for now, take my word for it. The first law in this case then simplifies to delta U is equal to Q, meaning that any heat added to the system will change internal energy. Okay, so here we see an adiabatic process, and this is a process where no heat is transferred into or out of a system. I've shown here a red line indicating an isotherm, and our purple line shows an adiabatic transition. Only work or mass are transferred for an adiabatic process, and these only generally occur when we have a very rapid change in the system. If there's more time, that's going to lead to more heat transfer, and that's not what happens. Okay, so the first law now simplifies then to delta U is equal to W. Work done on the system will increase internal energy, or delta U is equal to negative W, in which case work done on the system decreases internal energy. If we have an ideal gas behaving adiabatically, then we get this equation in which pressure times volume to the 5/3 power is constant. You don't need to worry about this derivation. It's not part of the IB Physics curriculum. If you're interested, I'm sure you can find a video on it somewhere. Note that the steeper gradient of our adiabatic process is due to a larger change in volume relative to the isotherm. Next, we have an isobaric process. This is a process in which change occurs under constant pressure. Again, we see no variation in the amount of pressure for this transition from our initial volume to our final volume. The first law in this case is given as Q is equal to delta U plus pressure times the change in volume. We will look at that a little bit more later, but you may have sussed out that that is work. That is correct. We know that work must be done due to our changing volume. So for an ideal gas, volume divided by temperature is constant. And again, we would have seen this in a previous lesson involving the ideal gas law. Next, we have work done on a closed system. And here we have an increase in the volume of contained gas at constant pressure. Okay, so the direction of the volume change is shown by this green area. So we have a small volume increasing to a larger volume. The arrow pointing to the right indicates an increase in volume. So our work done here must be positive, and this means that energy must be put into this particular system. For a closed system, the work done can be expressed as work is equal to pressure times the change in volume, and defining our variables. There we go. Positive work will occur when the system does work on its surroundings, and this will cause an increase in volume. Negative work occurs when the surroundings do work on the system, and this will decrease the volume of the ideal gas. So here we see a closed system, again, piston and our cylinder filled with gas. So if we change this volume, this will change the position of the piston by delta x. It's shown here as a D, but we can use our imagination. Any work done on the system then will be given by work is equal to force times a change in displacement of the piston. And we know that force is equal to pressure times area, so we can substitute that in. We also know that area times a change in distance is going to be equal to a change in volume. Hence, here is a very quick derivation that tells us that work is equal to pressure times a change in volume. And of course, defining our variables. There we go. All right, next we have work done on an adiabatic system. For this amount of work, we can calculate the area under the volume pressure curve, but this would require the use of calculus. You may be able to handle that using your math skills, but we don't need to know it for IB Physics. You could potentially be asked to estimate this area under the curve, but more likely you will be given that information. All right, my sources here include this textbook and a number of diagrams and images that I've mostly taken from Wikimedia Commons. Please donate if you use Wikipedia or Wikimedia Commons. And it was prepared using Google Slides, LaTeX, Desmos.com, Adobe Illustrator, among probably other software. Do not click like, do not subscribe, but please have a great day.